So the recording has started, and yeah, so I'm using this Zoom whiteboard. So the Laplace transform, okay, Laplace transforms, okay. So Laplace transform is defined as like this. So for example, if we have a function in t, so its Laplace transform is defined as from as an integral from 0 to infinity, and then e power minus st into that function of t dt. Function of t dt. Okay, so the Laplace transform of a function of t is uh, in another variable which is called as the s. Okay? So we call it as a function in s. Okay, so this is the definition of the Laplace transform. So in this Laplace transform, this function of the given function is multiplied by this e power minus st. So this multiplying function is called as the kernel. Okay, kernel for the for this transform. So uh, for some other transforms in mathematics, there are different kernels which are used, but for the Laplace transform, this kernel is used. Okay, e power minus st. So the Laplace transform is a interesting topic in mathematics, which is helpful in solving many uh, problems, especially the differential equations and the given, especially the differential equations and their initial value problems. And there are certain advantages of the Laplace transforms as well. Maybe the solution is a little bit quicker than the normal methods as well. So in order to apply the Laplace transforms, we need to derive certain formulas, okay? And if in the videos which I have uploaded over here, you will see that we have derived different formulas. So for example, one of that formula is the Laplace transform of 1 is 1 over s, okay? So this can be derived by this relationship. If you just integrate it, and then you will get it as 1 over s. Similarly, the Laplace transform of a function t is equal to 1 over s square, or the Laplace transform, if we generalize it for any integer value power of t power t power n, so it will be the t power n plus 1. It will be then n factorial maybe I'm thinking it's t power n, okay, t power n. It will be, yeah, t power n, it will be n factorial divided by s power n plus 1, okay? And similarly, we also know that the Laplace transform of cosine of omega t will be equal to s over s square plus omega square, and the Laplace of sine of omega t will be equal to omega over s square plus omega square. So all of these formulae can be derived by taking these integrals. Okay. Similarly, the Laplace transform of e power a t is equal to 1 over s minus a. Okay, it will be 1 over s minus a. Or the Laplace transform of e power a t times any function of t will be equal to that function with s replaced by s minus a. So these were the things which I derived in those videos. I would recommend you to look at those videos. So for example, now let's take one of the one of the derivations. For example, okay, we can start from 1. Okay, Laplace transform of 1 will be equal to, by definition, it will be 0 to infinity e power minus s t, and f of t is just 1. So dt. If you take the integral, so it will be e power minus st over minus s, and the integration limits are infinity to 0. So it will be then, so what will be e power minus s, and t is replaced by the infinity. E power minus infinity is, what is the value?
0.
Yeah, 0. And e power 0 is
1.
1. Okay, and then divided by minus s. So it will be 1 over s, as we can see from here. Okay, so this was for the e power 1 over s. And similarly for the Laplace transform of sine of omega t, we can find out. Okay, so Laplace transform of sine of omega t will be equal to 0 to infinity e power minus st sine of omega t dt. Okay, so now in order to evaluate this integral, we need to adopt a method of integration by parts. So I like this method for the integration by parts, which is called as the DI method. Okay, in DI method, I take over here maybe e power minus st as the function for the integration, and sine omega t as a function for the differentiation. Okay, so I differentiate sine omega t, it will be omega cosine omega t, and I will differentiate it one more time. So it will be minus omega square sine omega t. Okay, so it will be e power minus st over minus s, and then again the integral, it will be e power minus st over s square. Okay, now it will be a plus sign. So, and then additionally plus minus plus. So with this, now we can directly write this integral as follows. So it will be sine omega t times minus 1 over s. So minus 1 over s e power minus st sine omega t e power sine omega t e power minus st over minus s. So it will be s over here. Okay, like this. And now this term will be multiplied by this term. So it will be minus, and then it will be plus. So it will be a minus term. So it will be omega cosine of omega t over s square. Okay, so omega cosine of omega t over s square e power minus st. Okay, right, like this. So so both of these will have we will need to apply the limits of integration, infinity and 0. Okay, and then the last term will be the integral of this. So it will be minus. It will be minus. Okay, plus minus plus minus plus. So it will be plus into minus minus omega square over s square integral 0 to infinity sine omega t and into e power minus st into e power minus st dt. Okay, so the things have become a little bit messy. So this is the third term over here. Okay, this is the third term. So these two are the first two terms, and then this is the third term. So now we'll have to evaluate these terms. So for example, this first term will be 0 for infinity. For infinity, it will be 0, and for 0, it will be 0 as well. Okay, because for infinity, e power minus infinity will be 0, and sine infinity, because the sine term will always range between 0 and 1. Okay, so this term will be 0, and then for 0, sine 0 will be 0. Okay, how about this next term? So next term for infinity, it will be 0. Okay, and for 0, this term will be equal to, because cosine of 0 is 1, and e power minus st is also 1. So it will be minus and then is plus. So it will be plus omega over s square. Okay, it will be plus omega over s square term. So I don't have any space over here. So maybe I need to move to the next one. Okay, so let me, in the next slide, I will write down this. Okay, this one. So we started from here. Laplace of sine omega t, and that was equal to maybe 0 to infinity e power minus st, and sine omega t dt. And then now we have found out that in this previous right, that from this one we got a value of omega over s square. Okay, omega over s square. So this is omega over s square we got, and then this one we got. What did we get from here? This is omega square over s square. Okay, omega square over s square, and then this term. Okay, the term over here, which is the same as the term on the left hand side. So here, so it is omega square over s square 0 to infinity e power minus st sine omega t dt. Okay, let me show you again. Yeah, it is sine omega t e power minus st dt. Okay, so now if I have not done any mistake in the calculation, so what I can do is I can take this term to the left hand side. So the left hand side will become 1 plus omega square over s square 0 infinity e power minus st sine omega t dt, because these two terms over here and over here are same, so I can combine together their coefficients. So this is equal to omega over s square. So what is this term? This term is Laplace of sine omega t. So, and then this term then becomes s square over s square plus omega square. And then this is the Laplace of sine omega t. So this is equal to omega over s square. So now s square cancels with s square. So sine of omega, so this means that the Laplace of sine of omega t is equal to omega over s square plus omega square. So in this way, we have proved that the Laplace of sine is omega over s square plus omega square. Okay, so is it clear?
Yes.
Okay. So the same has been done in the uploaded video, but in the uploaded video, I did for the cosine of omega t. So uh, I over there, I just said that this process for sine of omega t is similar. So here I have done it for the sine of omega t. Okay, so similarly, there are some other derivations as well. One of the derivation is called the S shifting theorem. Okay, so what does the S shifting theorem? S shifting theorem is same as like this. Which one? Yeah, this is the S shifting theorem. Okay, which simply states that we know that the Laplace of f of t is f of s. But if f of t is multiplied by e power at, its Laplace will be f of s, but the s will be replaced by s minus a. So with this thing in mind, and then this theorem is very easy to prove. I have done it in my uploaded video. So we can easily find the Laplace of e power at times sine of omega t. Okay. How? So what will be the Laplace of e power at sine of omega t? We have just found out the Laplace of sine of omega t as this. Okay. But now sine of omega t is being multiplied by e power at. So its Laplace will be same as the Laplace of sine of omega t, but s will be replaced by s minus a. So its Laplace of e power at into sine of omega t, its Laplace will be then omega over s minus a square plus omega square. Okay. So similarly, the Laplace of e power at cosine of omega t will be equal to, because for the cosine, Laplace of cosine of omega t is s over s square plus omega square. Okay. So therefore, Laplace of e power at cosine of omega t will be, can anyone tell?
S
S
minus
minus
1
A.
Yes, s minus a.
over S minus A squared.
Yeah, s minus a square plus omega square. Okay, so by the same rule, the Laplace of e power at into cosine of omega t will be this. Okay, so now what I can do is I can show you the application of the Laplace. So one of the application of the Laplace is to find the solution of the initial value problem. Okay, so for finding the solution of the initial value problem, we must also know what is the Laplace of a first and second derivative of the function. Okay, so the Laplace of the, for example, if there is this function f of t, and then its first derivative is f prime of t, and the second derivative of is f double prime of t. So we know that how to find the Laplace of f of t, and by the same procedure we can also find the Laplace of f prime of t and f double prime of t by the integration method. However, I have done it in my uploaded video. So, but I can just tell you over here is that the Laplace of f prime of t will be f prime of t will be f prime of t will be equal to s times the Laplace of f of t, that is the original Laplace of the original function. Okay, Laplace of the original function minus the original function evaluated at a value 0, t is equal to 0. So this will be the Laplace of the first derivative. Okay, and using this we can find the Laplace of the second derivative, f double prime of t, and then that will be equal to s square Laplace of the s square Laplace of the function of t minus s times function evaluated at 0, and then minus f prime evaluated at 0. Okay, so in this way that will be the Laplace of f second derivative. Similarly, we can even expand it. So for example, the Laplace of the third derivative of t will be equal to s cube Laplace of f of t minus s square f evaluated at 0 minus s f prime evaluated at 0 and minus f double prime evaluated at 0. Okay, so in this way we can find the Laplace of the third derivative as well. But anyway, we will normally not go beyond the second derivative in this case. So we can use this type of concept to solve the numerical question, sorry, not the numerical question, the initial value problem. So for example, the initial value problem is over here is say if y double prime plus y prime plus 9y is equal to 0. In this case, the value of y at 0 is 0.16, and the value of y prime at 0 is 0. Okay, so using the Laplace transform, solve this initial value problem. Actually, you can solve this problem by using the characteristic equation method, and you can find it. But let's but for the Laplace transform, how you will solve it? So you will take the as a first step, you will take the Laplace of this equation. Okay, so Laplace is a linear function. So Laplace of the function of the components of the function, Laplace of a function which has some components is equal to the Laplace of their components. So for example, if you take the Laplace of the whole left hand side, it will be equal to the Laplace of y prime plus Laplace of y double prime, Laplace of y prime plus 9 times the Laplace of y. Okay, so and similarly for our notation, we will represent the Laplace of this small y with the capital Y. Okay, with the lowercase y. For lowercase y, the Laplace will be represented by an uppercase y. Okay, so we take the Laplace of this. So this is the y double prime. So its Laplace will be given by this equation. Okay, so if we take the Laplace of y double prime, so it will be s square, and Laplace of f, so Laplace of y double prime, so that we will represent by y, and minus s, and then y evaluated for 0. Okay, and minus its first derivative also evaluated for 0. Okay, so for y prime, so we will use this first formula, so it will be plus s times Laplace of f is y, okay, and then y evaluated for 0, so minus y evaluated for 0. And then it is plus 9y, so plus 9, and Laplace of y is represented by capital Y. And then Laplace of 0 is 0. So remember that Laplace of 1 is 1 over s, Laplace of 0 is 0. Laplace of 0 is not like 1 over s or something like this. Laplace of 0 is 0. So this is the first step. And then in this step now we will collect the terms of y, okay. So this is s square, and then another term over here is it has s, and another term over here it has 9. So now we have combined together these terms of y. And now next is s over here, and y0 is 0.16, and y prime of 0 is 0, so it is 0, and then this y0 is 0.16 is equal to 0. So now we can say that this is an equation 0.16 s plus 0.16 over s square plus s plus 9, okay. So in this case, in every Laplace transformation solution for the initial value problem or for the differential equation, we will find an expression like this. So we will have to, this will be our objective, in the first objective to achieve. So we have to find an algebraic equation. So this is an algebraic equation in terms of capital Y, okay. Now in the next step, which I can, maybe I have space over here, I can represent over here. In the next step, we will have to find the inverse of this, because this is the function in terms of s. So we have to find the inverse of this right hand side, so that we can find the answer back in terms of the function which will be t. So if, for example, if Laplace of y of t is equal to y, so the inverse of this Laplace inverse of y will be equal to y of t. So we are going to find the inverse, and then in the inverse we will find the answer in terms of y of t. But for finding its inverse, we have to write it in some, we have to do some manipulation. So this is the most difficult part in the Laplace transforms, because sometimes it does not simply work. So in this case, I can take 0.16 as common. So 0.16 as common. So it will be s plus 1 over s square plus s plus 9. I think in this case, given the formulas for the Laplace we know, I can try to complete the square in the denominator, okay? So what I can do over here is, I can focus on the denominator first. So I think I will just, you will understand it when I will write it like this. So it is, can I write it like this? Okay, can I write the denominator like this if I write it directly like this? Answer me.
Yes.
Is it okay to write it like this? Yes, so I have heard someone has said yes, okay. So it's understood. So basically we have completed the square. So it is s square plus s, and then we have added 1 by 2. So it is s plus 1 by 2 square. And then for the equality, we have to subtract 1 minus 1 by 4 from here. So 9 minus 1 by 4 is 35 by 4. So similarly, in this case, on the top, I can write, if I take 0.16 as outside over here. if I take 0.16 as over here, so it is s plus 1, it is s plus 1. So I can I write it like this, s plus 1 as s plus 1 by 2, and then also 1 by 2, okay? So I can write it like this. So in this case, what I have done over here is, so I can further simplify, further write it like this, s plus 1 by 2, and then it is s plus 1 by 2 square plus under root 35 by 2 square, okay? Okay, so now I have this term. So now what is left is 1 by 2 into 0.16. So it will be 0.08, okay? If I combine these 1 by 2 and 0.16, it will be 0.08. And now over here, can I write it like this? Under root 35 by 2, okay? And similarly, under root 35 by 2, I divide it over here, and then I can write it like this, s plus 1 by 2 square, and then under root 35 by 2 square. So can I write it like this? Okay. And then over here, I will close the bracket, okay? My space is really very narrow over here. So here you can see it's like this. So, but by writing like this, so now I have wrote it in a standard form. So 0.16. So in this case, what is this? Is if you just take s plus 1 by 2 as, say, s, okay? So it is s square, and then this take this term as the omega. So it will be s square plus omega square. And over here it will be s. So this is the term in this over here, it is simply the cosine of s, okay? It is the cosine of this omega t. So this is the Laplace of the cosine. So, but it is with the shifting of plus 1 by 2. So it will be represented as e power minus t by 2, okay, by the shifting theorem, and it will be cosine of omega t. Omega is under root 35 by 2 t. And how about this next term? So it will be then 2 will go up, so it will be 0.16 divided by under root 35. And how about this term? So it is under root 35 by 2 is in the numerator, and then this is the one term over here. So this is the e power minus t by 2 sine of under root 35 by 2 t. So this was the Laplace of cosine sine of omega t with the shifting of 1 by 2. So in this way we can find the solution. So that will be the solution in terms of, here we have written the solution in terms of s. So this will be the solution in terms of y of t. Okay. So this will be the solution. Is it understandable, or anything? Is there any doubt? Is it clear? So remember that we have simply applied 3 formulas over here. So one of the formula was Laplace of cosine omega t is equal to 1 over, s over s square plus omega square. And the other formula which we applied is Laplace of sine of omega t is equal to omega over s square plus omega square. And then when the shifting, when, for example, cosine of omega t is multiplied by e power minus 8at, so its Laplace will be then s minus a over s minus a square plus omega square. And then for similarly for the Laplace of e power at, sine of omega t. So it will be omega over s minus a square plus omega plus omega square. Yeah, okay. So it will be plus omega square. So using this and then the manipulations of their, with the manipulation of their coefficients, then we can see that this is the answer. Okay, so in this case, we have solved the initial value problem. So you can see that the solution of the initial value problem involves certain steps. So first of all, you take the Laplace of the initial of the differential equation, you convert it into the S, and then you represent all the S functions on the right hand side of the equation. On the left hand side, we have only capital Y, and then you take the inverse of that function, which is, I have said that, which is the most tricky part, or maybe sometimes it's difficult as well to find the solution. So here you can see that we have found the solution for the initial value problem. So that's all I wanted to discuss today. So if you have any questions, then let me know, and then I will upload more videos, and then I think I would recommend you to look at those videos regularly so that you can catch up this topic quickly. So do you have any questions?
No questions.
No questions? Is this topic clear? Is this topic clear?
Yes.
Okay, then it is good. So if this is, if there is no more question, then maybe I can declare this class to close, or then we will meet on next, the coming Friday, the day after tomorrow. Okay, then, bye-bye.
Thank you. Bye.
Bye. Thank you.
Goodbye.
Bye-bye.